Hello, welcome back. Now in this video, we will continue with the lessons on cycle. Now in the other video, we talk about cycles, but we talk about it in the life science context. In this one, we'll talk about cycles under the physical science. Let's get started. Let's begin with question 7. Yelin lowered an empty glass with a small ball into a container of water until it touched the bottom of the container. She observed that the water level inside the glass was not the same as the water level outside. So what she means here is there's a water level outside, which is this one, and there's a water level inside, which is this. Right? The water levels are at different positions. The ball still floated on the water as shown below. See, a little bit of the ball was floating on the little bit of water inside. What could be the main reason for the difference in the water level inside and outside the glass? Now, what is in this empty space here? Very clearly, air is occupying the space inside the glass. Now, this question is on the topic of matter, about states of matter and the property of matter. So, this question is more on the properties of matter. And one property of matter is matter occupies space, right? So here the air occupies the space inside the glass. That is why the water outside cannot just rush in. Second property is this. Now, air is a state of matter and air is a mixture of gases. Air can be compressed because air is a mixture of gases, and because gases can be compressed. Since gases can be compressed, that's why some water could enter and push and compress some of the air. It cannot go all the way up because air still occupies space inside the glass, but it allows itself to be compressed very slightly. So what's the main reason for the difference in water level inside and outside the glass? Well, it's because the air trapped in the glass occupies space. So if we were to poke a hole on top, then the air inside can be pushed all the way out by the water going in. If the air can be pushed out, then of course the water outside will go in until it is all level. Okay, until it's all level. But that's a different story. Now let's take a look at question 16 now. Earlier we talked about air occupying space, we talked about matter occupying space, so things like solids, liquids also occupy space. Now in this experiment, Ella used two identical syringes. Each syringe was covered with black paper, so we can't see through it to see whether whatever is in the syringe, is it a solid or is it a gas, mixture of gases like air, or is it a liquid? So we must depend on certain observations that we can observe. And what is that? She pushed this plunger as hard as she could. Then she measured a distance d. This is the distance d. Now, if this distance d can be reduced, that means that she's able to push in and compress whatever is inside. If it can be compressed, then it will be a gas that's inside. There's air inside. Alright, let's see. She pushed each plunger as hard as she could. So if it contains a gas inside, it contains air inside, then of course she can push it in. Alright, push it in. So if it still remain at 10 cm, it means she cannot compress air, which is wrong, right? Air can be compressed, so this is wrong. This is wrong. Now, 0 means she compressed air until air disappears. But air cannot disappear because air is a mixture of gases. Gases occupy space. Even if we can compress it, air still occupies some space inside. So this is not possible. So what is possible is, well, you can compress a little bit and they still leave 5 cm. So you can push into 5 cm. So distance d measured becomes 5 cm. Plunger reaches all the way here. Alright, and of course inside it moves all the way somewhere here. If it contains water, then of course you cannot compress it at all. It still remains at 10 cm, right? 10 cm if it contains water. So cannot be compressed. So answer is 3. Now let's go to the next question. This is question 41 on page 84. An experiment was set up using a sealed metal container which holds 60 cubic centimeter of water and 40 cubic centimeter of air as shown below. Now 10 cubic centimeter of water was removed from the container through the tap, and 30 cubic centimeter of air was pumped in using pump P. Now, this is a very standard kind of question you have seen many times before, like try to pump a basketball or try to pump air into a container such as this. Remember, air can be compressed. Liquids like water cannot be compressed. So what will be the final volume of the air in the container? Well, let's remove some of the water, right? Because we were told that there was at first 60 cubic centimeter of water. Underline to help yourself to remember what you've read. 10 cubic centimeter of water was removed, so minus 10, leaving 50 cubic centimeter of water inside. So it's like this, it's like, oh, some water left, so so let's say I remove this 10. This 10 cubic centimeter of water was removed. So I'm going to remove it using my correction tape, so it's very clear to all of us there's less water inside now. Now there is more space above, isn't it? More space above. And then you pump in 30 cubic centimeter of air. But I don't really care so much how much. They can pump in 3,000 cubic centimeter of air. It doesn't make a difference. The volume here will not change because whatever gas that goes in will be compressed inside this solid container. So let's take a look at the container, right? It says that this container at first contains 60 cubic centimeter of water and contains 40 cubic centimeter of air. So at first, the total volume of the container is actually equals to 60 plus 40 equals to 100 cubic centimeter of water at first. 100 cubic centimeter. It contains 100 cubic centimeter of water and air at first. Then you remove away 10 cubic centimeter, leaving here 50 cubic centimeter of water. Since the total volume is at 100, there's 50 here, so there's 50 here. So even if you can add 30 in, it will not increase this to 80. Alright, so answer is 50. Now let's go, which is number 2. Let's go to the next question, which is question 35. For this question, we are looking at changes of state of water. So water goes through different stages from, let's say, ice, solid, gains heat, it melts and go into liquid state. Liquid state gains heat, then it evaporates into gas. Or you heat it high enough to the boiling point, it can boil into a gas. So which of the following describes A, B, C correctly? Let's take a look. So I like to go from solid because I'm a pretty solid kind of guy. So solid melts, becomes a liquid. Liquid must have done something, become a gas. So this must be something like gaining heat. So it must have evaporated. So let's see, C must be evaporated. And for gas to return to a liquid, it must have lost heat to some cooler surface. So this part is where I talk about condensation. So B must be condensation. Right, we got our answer. Answer is 1. But we always want to make very sure. So let's move to the last step. So for liquid to become a solid, it must have lost even more heat. So that process is what we call freezing. Yep, it is freezing. Yep, answer is 1. Let's go to the next question now, and that will be question 12. And question 12 is also talking about freezing. Now, do remember that freezing point and melting point are exactly the same. For example, the freezing point of water is at 0 degrees Celsius. The melting point of ice is also at 0 degrees Celsius. In this case here, they give you 3 unknown substances. They're definitely not water because their freezing point are all not at 0. Okay, so we don't care what these things are. Just know that the freezing point is at 5 degrees Celsius for A, 30 degrees Celsius for B, and 120 degrees Celsius for C. Which of the following is correct? Now, you say A is a solid at 30 degrees Celsius. Now, I'm just going to do a very simple working using 3 different colors. So, this line represents A, this one represents B, and the next one represents C. Okay, is C. A, B, C. For A, we are told that at 5 degrees Celsius, it will freeze. So the part below here definitely is solid. When it reaches 5 degrees Celsius, it will melt and becomes a liquid. So anything above here will be liquid. For B, I can't write down for gas because I'm not sure what's the melting point. Oh, sorry, what's the boiling point, so I can't tell where is the gas part. Now for B, it says freezing point is 30, that's higher than 5, right? So here it's at 30 degrees Celsius. So all the parts below here will be solid. The parts above will be liquid. Finally, for this C, at 120 degrees Celsius, anything below here will be solid, and all the parts above here to an unknown degree Celsius that I don't know, all these will be liquid. Now that we have this, let's check. A is a solid at 3 degrees Celsius. 3 degrees Celsius is here. Yep, that is true. Let's check. A and B are both liquids at 28. At 28, A is a liquid, 28 is somewhere here. However, at 28, B is still a solid. So this is wrong. B and C are both solids at 130. At 30 or below, B is a solid. At 130 is above here, B is already a liquid. So this is wrong for B. C can be a liquid at 120 or a gas. No. At 120, C can either be a solid that is melting or a liquid that is freezing, but it cannot be a gas. Alright, so this is false. Answer is 1 for this. Let's go to the next question, question 22. Question 22 is this. Now before we go on, do you observe something? This kind of question about melting point, freezing point, finding the state of the substances, do you see a certain repetition, a certain similarity? If you do, that is because it is true. This kind of question basically look like that. Alright, you can't change it very much because this is a good thing for you, because if you know how to solve this kind of question, then, and it comes up pretty often, just make sure you know how to do it. Substance X freezes at 63 degrees Celsius and boils at 759 degrees Celsius. So go back to the working. I'm going to just draw one line to represent this substance X. So this is my X. This is my freezing point at 63 degrees Celsius. So anything below would be solid. What is above here will be liquids. And all the way up to the boiling point at 759 degrees Celsius. And any part above here will be gas. Now we need to look at the state of the substance at the different temperatures. At 70 is between these two. It's a solid, they say. That's wrong. If it's at 70, that is somewhere here, then X is a liquid. So this is wrong. Next one. Oh, still wrong. Okay, at 70, it is a liquid. Yeah, that's true. How about this? Is it a gas at 500? 500 is somewhere here. It is still a liquid, not a gas. Alright, it's only a gas above 759. So this part is wrong. At 70, it is a liquid, and that's true. At 500, it is also a liquid, that is also true. Answer is 4 for this question 22. Now let's go to the next one, question 25. See what I mean by very similar looking question. These are questions from different years between 2006 and 2010. Now we have another substance X. Okay, I'm confused which substance X we're talking about. Now let's use a different color to represent it. And we have freezing point is at 40 degrees Celsius. Okay, so anything below here is a solid, and then the boiling point is at 180. So this is my 180 degrees Celsius. So anything above here is gas. In between here will be liquid. Now, which of the following shows the state of substance X at 30 degrees Celsius and 200? At 30 is below 40, right? 30 will be here. So this will be solid at 30 degrees Celsius. At 200, that is above 180, that's 200. And this is the gas. So I'm going to check this now. At 200, it should be a gas. At 30, it should be a solid. So answer is 1 for question 25. Let's go to the next question, question 42. Okay, let's start from the top. Matter. Does it have, and sometimes we just don't read like this. Look at the whole question first so we can look at it more intelligently. We ask to find out the states of the different things like P. What is question X and what is Q? With things like air, water, oxygen, oil, conductive property of materials, and different materials itself. Alright, so let's take a look. Does it have a definite volume? No. So gas is here. This part is either solid or liquid, right? We're not sure what it's talking about. Does it have a definite shape? No definite shape and not a gas. So P must be a liquid. Let's check what is a liquid for P here. Well, it is not air, it is not oxygen, so it's either water or oil. Next one. So does it have a definite shape? Yes. So all these things must be solids now. Must be solids. And it says this question and the answer is no for rubber. So what is it? Is it a magnetic material? No. That's true. Is it a magnetic material? No. That's true. So this one doesn't help us to get the answer because it's exactly the same statement. But for the next one, it does. Yes. So what is a magnetic material? Iron and steel. I have iron here, aluminum. So sorry, that is not a magnetic material. So the answer for this is number 2. Let's go on to the next question. And now we're going on to water cycle question. And that will be question 3. Well, this is question 3, a water cycle. Now, for any functioning water cycle, there should always be a sun somewhere because you need the heat from the sun to help the water to evaporate. So A is evaporate, right, into water vapor. C, water evaporates into water vapor. So we have either 1 or 2. And when water vapor rises high up into the sky, touches the cooler part of the sky, it then condenses into cloud, which is actually tiny water droplets. So these are liquids, right? So this process here is condensation. So B is condensation, right? Answer is 1. Let's go to the next question, and that's question 32. These are the slightly harder kind of questions because it requires you to pull in information that have been presented to you in different ways, through a diagram, through tables, and there are also words. So let's take this slow and easy, and if I were you, I would use things like highlighter to help me to pick up information. So yeah, he did this experiment, wet cloth. Okay, wet cloth, pot with tiny holes, pot with tiny holes, wet sand. So I see there's some water somewhere. At this point in time, I'm still not quite sure what is the concept being tested here. Tiny holes mean it allows things to move in and out. So what is moving in and out? I'm not quite sure yet. See a thermometer. So is it about heat or not? Or is it about evaporation? He placed the setup in a dry place. Okay, that's a dry place. So no rain, no puddle. He recorded the temperature of the air inside the small pot, right? And over time, the temperature actually decreased. Oh, temperature decreased. What could have caused the temperature to decrease? Now, we talk about changes in state, right? Solid, liquid, gas. So let's focus on this part right now, because here I see wet means there's water here, there's water in the sand, water in the cloth. So the water, which is the liquid, must have evaporated into a gas. And the process of evaporation, right, requires heat gain by the liquid. The liquid must gain heat. But where's the heat from? There is no heat source, right? No, there is. The surroundings. All these parts, alright? Anything that surrounds this wet cloth and the wet sand can give it heat. So as this moisture inside the sand and the moisture in the cloth gains heat from the environment loses heat and becomes cooler. Only the immediate environment. So therefore the temperature drops because the heat inside went on to evaporate the water inside the sand. The heat inside went off to evaporate the water inside the cloth. So I will see things like water evaporating from wet sand. Seems to make sense. Alright. Now let's take a look at the rest. So right now my answer is number 1, but we need to check the rest to see if it makes sense. Heat is conducted to the thermometer. That does not explain drop in temperature. If you're talking about thermometer gaining heat, we should see temperature increasing, right? So I don't see that happening here. So this one doesn't make sense. Water vapor condense on the wet cloth. Water vapor condense in the wet cloth. Should the wet cloth be evaporating into the moisture evaporating into water vapor? So this one doesn't explain why the temperature is dropping. Temperature drops because the liquid is gaining heat from the environment. So the environment is losing heat to the water. That is the concept. The environment is losing heat to the water, so the water evaporates. Going back to number 1. Last one, wet sand acts as a poor conductor of heat. Still does not explain the drop in temperature. So the answer is 1. Let's go to the next question now. And that is question 11. Now you need to be very familiar with water's special temperature. Water's special temperature, which is 0 degrees Celsius and 100 degrees Celsius. Alright, this will be the boiling point, and this is your freezing point or melting point. And water is special at the freezing and melting point because if, let's say, ice is melting, alright, so long as there is still some ice around, the temperature of the melting ice plus water is still at 0 degrees Celsius, theoretically. So in this room, Ling E heated a beaker of tap water for 20 minutes until it started boiling. She continued boiling for a further 10 minutes. Which one of the following graph shows the change in the water temperature over the 30 minutes correctly? So the story here is, at first, it was tap water. So tap water is at room temperature. Okay, room temperature. But this one shows the starting point is at 0. At 0. Your tap water doesn't come out at 0 degrees Celsius, doesn't it? Okay, so therefore straight away you know 1 and 3 are wrong. Okay, next part of the story, it started to boil, started boiling. So boiling must be at 100 degrees Celsius. So this one starts at the room temperature, right? These two boiling, I'm going to assume this is 100 degrees Celsius. Okay, very good. And water temperature, when it hit 100, it cannot go up higher. So it should remain constant, a plateau like this. This one, something is wrong. It's showing the temperature can increase above 100. No, that's not the case for pure water. So this is wrong. So answer is 1 for question, answer is 2 for question 11. Let's go to the next question. Question 10. Saying, place 2 identical open bottles near a window. When I see water in bottles near windows, I think of rate of evaporation. There are 3 factors that affect the rate of evaporation. I remember it by saying wet. Wet stands for wind, exposed surface area, and temperature. Saying place these bottles where there's sunlight. Now, light doesn't cause water to evaporate, but sunlight means there's also heat energy there, right? In the energy that comes from the sun. He filled one bottle completely with liquid A and filled the other bottle completely with liquid B. So like there's a bottle here, A and B, right? 2 different kind of liquids. The next day he observed the bottles were no longer full. So at first it was full. Sorry, this is not full. At first it was like completely full. So all the way to the brim. Alright, to the brim. Then after one day, the water level drops. There's a decrease in the water level. So what happened? So both liquids evaporated. That is true. Arsene can conclude from this experiment. Now, do we know whether liquid A evaporates faster than liquid B? There is no information given saying which container has less water. There's no information, right? So C is not possible. So this is not possible, this is not possible. Now, then we are left with 1 or 2. Let's check B. Both liquids need sunlight for evaporation. Now, this is the tricky part. When we talk about sunlight, it's referring to light energy, not heat. Okay, light energy, not heat. So talk about this, then this is a wrong conclusion because I can evaporate water without light. For example, I can put the same container filled with the liquid, okay, then I place it inside a dark room. So there's no light at all, a dark room, no light. I place this container of water over a hot plate. I turn it on until it's very hot. Will the liquid inside gain heat and evaporate? Of course it will. Is there light inside? Of course there isn't. So, to say that liquids need sunlight for evaporation, well, that's just not true, and this experiment doesn't show it. So B is false. Alright, so the answer is number 1 for this. Let's go to the last question, question 23. Another question about rate of evaporation. Remember what are the factors that affect the rate of evaporation? How can we remember it? W-E-T, right? W stands for wind, E stands for exposed surface area, and T is your temperature. So Dina carried this experiment using setup A. There's a glass of water. There are 2 openings for gases exchange. Here there's a fan inside. Oh, fan. Therefore, I see this happening. There's wind here in B. So exposed surface area seems to be the same. Exposed surface area refers to how much of the water surface is in contact with the air. Well, these 2 green lines seems to be the same in length. So exposed surface area is equal. Temperature, well, they seem to be in the same place to me. It's not stated in the question. So I'm going to assume that they are in the same place. So this seems equal to me. So since B has 1 more factor to cause it to evaporate faster, which is the presence of wind, I'm assuming the fan is switched on. Therefore, the water in B must be less. Okay? So these 2 are wrong. And why is it less? Because the water evaporates faster. So answer for 23 is 1. Alright? Thank you for hanging in there. You are awesome. I'll see you in the next video.